afternoon. My name is Barry Fitzgerald, and you're very welcome to the Stories of Change, which is part of the Drivers of Change program and initiative brought to you by TU Eindhoven as part of Dutch Design Week 2020. Now, I'm sure that many of you are aware of this already, but Dutch Design Week 2020 is completely online, completely virtual, and the Drivers of Change is also virtual as part of this program. Today, Friday afternoon of Dutch Design Week, we have a very interesting talk as part of the Stories of Change. Over the course of this week, you've heard a number of researchers and developers who are based or affiliated with TU Eindhoven speaking about their work and how they can impact on various aspects of society. Now, today we are going to be looking at something which I think is quite fascinating and very, very interesting, is the idea of soft robotics. And the title of the talk is Shining a Little Light on Soft Robotics. And as we're going to find out, we're going to learn a little bit more about the type of materials you could use to make such robotic devices and where exactly we could actually use them in society. Our speaker is a PhD student based in the Department of Chemical Engineering and Chemistry at TU Eindhoven, and they are Marina Pilz Da Cunha.
Right. Thank you, Barry, for the introduction. So in the presentation today, I'll be talking about bio-inspired materials that can respond to light and how these materials will actually impact the future of soft robotics. To illustrate a little bit how how our research on soft robotics is inspired, I always like to look at nature. So in nature, we see many examples of materials and organisms that can interact with their environment. And in this interaction, they use triggers to help them perform a certain function. So examples of this can be plants that will mechanically deform in order to follow the sun to help them perform the function of photosynthesis, for example. Other plants use humidity as a trigger to help their seed dispersal, thus helping the species in the proliferation. And maybe the example that's closest to us is our own skin. So our own skin is not only a barrier to the environment, but it can also help us in temperature control and changes pigmentation according to sunlight. So if we look at all of these really nice examples in nature, and now we look at our man-made materials, we see that our materials are quite static. And by static, I mean that they are not really responding to their environment. They don't really have the capability of self-healing, like our skin, and they're usually difficult to recycle. But if we now think about nature and our materials, and we could learn from nature, so implement the stimuli responsive that we see in nature into our materials, we can think of many applications in which this would be really interesting. So a few applications can be robotics, responsive surfaces, such as for haptics, or even smart textiles that would help in our thermal control, our thermal comfort. And in my research specifically, we've been looking at how stimuli-responsive materials can be applied in robotics. And why robotics? Well, robotics has been undergoing a kind of a transition from the conventional hard robots that we know, which are composed of stiff metallic segments, into soft robotics. And soft robotics, the materials that are used are soft in nature. And this is actually really interesting for applications in which there's a lot of interaction with humans, or in which the robots need to perform fragile tasks with fragile objects, such as picking up an egg or navigating in difficult environments. And for soft robotics is also going into micro-robotics. And it would be very interesting to remove tethering from these devices. So removing any kind of wire that is attached to the device and external control systems. And in this way, we also wouldn't need to have any electrical circuits embedded in the devices themselves. This would be really interesting. And this is where stimuli materials can come in play. So imagine using stimuli such as light, humidity, temperature, or magnetic fields to drive these mechanical deformations that would lead these soft robots to perform tasks like walking or grasping objects. And in my research, we've been looking specifically at light as a very interesting stimulus. So light provides us with an immediate and high degree of control, and we don't need any kind of bulky external setups. All we need is light sources to drive these devices. And basically, the polymers that we're using, in very simple terms, are comprised of long rod-like molecules in which we can manipulate so that we know and manipulate their orientation. And once that orientation is set, we can in fact freeze in that alignment into a network. And how we do that is through a process of polymerization. So we're basically freezing in how these molecules are oriented. So in the macroscopic scale, these films, these polymers, they look like very thin polymers. And by basically playing with the molecular alignment within the thickness of these polymers, we can encode a certain kind of deformation when these materials encounter changes in their environment. So one example is implementing the response to heat. So by tuning in the molecular alignment of these molecules throughout this polymer film, we can drive temperature response. So in this video, you're going to see a bent polymer film in which it encounters hot water, and by feeling that increase in temperature, the film immediately rolls out and responds. And this response is immediate and is reversed when the temperature is cooled down. So we can imagine that these smart polymers can be used in applications in the future, such as smart curtains. So imagine that curtains would sense themselves any kind of change in the environment, and without having any human controlling or turning it on, these curtains would immediately unwind upon increase in temperature, and when temperature decreased, they would rewind back up. But like I said before, we're interested mostly in light response. So how do we implement light response in such smart polymeric films? You do this by implementing or doping into the polymer film during fabrication photosensitive molecules. So these molecules, what they essentially do is that they absorb incoming light, and that light triggers a mechanical deformation of the molecules. And through the molecular organization of the molecules within the polymer, we can translate the molecular motion into a macroscopic behavior. So this can be seen, for example, in the unbending or bending or twisting of a film. So it's going from molecular motion into centimeter scale motion. And in this video, you can also see a polymer film, which is resting on a surface. And upon illumination with light, the film completely unbends. And when light's turned off, it bends back. So light is giving us fast response and allows for local adjustability, because we can use focused light to simply excite only parts of the film. And we have a high degree of control, because we can use low intensity lights for low amounts of deformation and high intensity lights for high degrees of deformation. But what's interesting is to try to transform this simple motions, such as bending, unbending, into actual functions in devices. So translating this simple deformation into soft robotic devices that are functional and can perform tasks, just like we see in organisms in nature. So one of the first tasks that we wanted to mimic is the grasping ability of organisms. So to do this, we used a very simple design. So it is a light responsive film with a tuned and architectured molecular organization, so that when no light is shining on the material, it is closed. And when light shines on the material, it opens up. Additionally, we have used also magnetic responsive rubber coated on the middle section of the film, so that the film can also be magnetic responsive. So the main idea of this design is the following. So the idea is to have a gripper which can be directed to a target. We then use light to open up the gripper, grasp whatever object the cargo is, and with a magnet that is then outside the enclosed environment in which the gripper is in, we can guide the gripper, which is loaded with this cargo, to any kind of location, and then subsequently use light to release it. So this is quite interesting, because you do not need wires, you do not need any human intervention for the device, while everything is enclosed in, let's say, a glass container. And in this video, you can see exactly that. So this is the gripper in action. And we use a magnet, which is outside the container, to guide the gripper towards the cargo, which is now here, a styrofoam object. And then with light, we can trigger its grasping or release. And because of magnetic guidance, we can also have completely rotational freedom. So we can move around corners, we can fit the device through openings, and have complete versatility of movement. So this device is quite simplistic in nature, and we wanted to take it a step further. Again, thinking about how animals move around and perform tasks. So our next step was to basically create an assembly of these smart materials. So thinking of an ant's ability to walk by controlling each movement of its legs, we did something similar with these materials. So we created a soft robotic device that's composed of quite a few light-responsive films. And basically, the device has 4 legs and a few sets of arms. So both the legs and the arms, they contain different photosensitive molecules. And that means that we can use different wavelengths of light to basically control the legs and the arms independently from each other. The hub of the material is not responsive, and it's basically just acting as a connector to all the pieces. So by using 2 light sources, we can place this little soft robotic device on a surface, and by just using these 2 lights, we can control the locomotion of this object. So we can make it move forward, backwards, and sideways. And the mechanism for locomotion is basically comprised of a few steps, a few elimination steps that can be changed in order to change the direction of the device. And this can be done so that the material can move around corners. And what's also nice to note is that this is a very simple device, and it weighs 20 micrograms, and there is no electronic circuit on board, and there is no wires attached to it. So it's completely untethered. Now, if we think back of the ant is able to not only walk, but it's also able to transport cargoes. So this was also something we wanted to do we wanted to have our device do. So what we do is that we loaded it with a cargo, and here it's just a styrofoam object, and our soft robotic device can still walk while carrying this package, and it walks towards a destination which is supposed to be unloaded in. And by using light, we're basically controlling the legs to steer locomotion. And when the soft robot arrives at its destination, we can use a different wavelength of light to steer the arms, and these arms would then unload the cargo onto its desired destination. We know that Eindhoven has a robotics team for playing football, and here this is where we can be creative with our soft robotic device. So we're just thinking in the future, maybe we're going to see light-driven soft robotic devices playing football here at the university. So this device shows that by using constructive actuation of different materials, we can perform functions. And one of the other things that we were interested in is, can we do the same thing as this robot does, but now underwater? Can we perform tasks when the soft robotic devices are completely immersed underwater? And to do this, we didn't take inspiration from ants, but we went to another organism in nature, and these are coral polyps. So colonies of coral polyps are composed of small organisms called the individual coral polyps, and they have quite a simple architecture. So they're made up of one stem that can move in any direction according to the currents in the ocean. And on top of the stem, we find tentacles, and these tentacles help the polyp capture nutrients in the water. So inspired by this design, we went on to create our own artificial coral polyp. And our artificial coral polyp is composed of a magnetic pillar, the same material that we use for our gripper. And this magnetic pillar is less than 1 centimeter high. And on top of it, we place light-responsive films. So the main design idea for this device was that through magnetic-driven motion, so by having a magnet rotate under our artificial polyp, we can drive the rotational motion of the stem. And after additional to this rotational motion, we can also steer light-driven opening and closing of these tentacles in our artificial polyp. So to demonstrate what this device can do, this video shows our artificial polyp submerged in an aquatic medium. And upon rotating a magnet underneath the polyp, we can steer and create a flow which will attract pollutants in the water. And in this case, we used oil droplets to signify these pollutants. And with light, we can subsequently grasp these pollutants or release them. And then through magnetic motion, we can then again steer these pollutants away from the polyp. To try to understand a little bit more about what's happening in the fluid while this polyp is in action, we've done some computational simulations in which we model the polyp rotating within a finite container filled with water. So these computational simulations really help us understand what's going on. So if you look from the top and we see our container, the arrows in the presentation, they're showing us the directionality of the fluid flow once the polyp starts spinning. So here we can see and actually confirm that our experiments that bodies of water or particles and pollutants that are within the container will experience an attractive flow towards the polyp during this motion. And through these computational simulations, we can also investigate how the architecture and the design of the polyp impacts the kind of flow that we're making. So by using light to control the degree of bending of these arms, we can actually control the velocity of the fluid within the container. So this was quite nice for us because it's additionally to changing the velocity of the magnet turning, we can actually use light to control velocity. So if you want the fluid to start spinning faster, we simply have to do is shine light on the polyp, and this will change then the velocity that the fluid is moving. And in this work, we show exactly how computational simulations go hand in hand with their experiments in the lab to bring more understanding to systems. So overall, the artificial polyp, as well as the walking robot, show us how inspiration from nature, together with using stimuli-responsive materials, leads to the development of new soft robotic devices that can perform functions without any need for tethering, and which is quite interesting for many applications. So where are we now? So in the beginning of the presentation, I brought your attention to how the materials that we use in our daily life are quite static, and they don't really perform a function and don't adapt to their environment. And then I went on to show you how we can make and fabricate polymers that will respond to light and heat. And recently, we've also shown how you can take these static polymers, PET, for example, which is the common material that you find in plastic bottles. And by a simple spray coating method, you can now make this otherwise static material into a responsive film. And because of the robustness of the PET, we can then create novel kind of actuators with different kinds of shape, which mimic structures that we see in nature, and subsequently then use light to actuate them. But where is the future heading? Where are these soft robotics devices leading to us? So further research and development on both the materials as well as ways and designs to integrate them into single soft robotic devices can lead to applications such as self-cleaning surfaces, which may help keep the efficiency of solar panels, or in water purifications, or even in the future, we may have biological applications for soft robots, in which we see soft robots maybe transporting cells from one place to another in organ-on-a-chip applications, for example. So with this, I hope I've given you an insight into the development that's been going on in our group and provided some inspiration for the future of soft robotics. Thank you for your attention.
Yeah. First, well, I'll start where I started again. Marina, thank you very much for a very interesting talk. It was very, very fascinating. So I'm going to cut to the chase. I see there are a lot of questions from the audience, which is fantastic. I have one question, and my question is this for you. So at the very end, you talk about applications. Is there any way that you could imagine these type of robotics being used to address issues with problems in populations of certain species? Because I can see what you're actually making are kind of replicants of, almost replicants, in particular of the underwater application of a particular species. Could you envisage these maybe being even used to try and help with repopulation of a certain species in a certain environment that has undergone some environmental damage or some sort? Because they're effectively like, as I say, they're like duplicates of, in some way, some of the things they can do. Is there any way that that could be a potential application? It might be a little bit outside what you've worked on, but
yeah, so
it'd be
this is
interesting
not
to hear
something
what
that
you think.
we've really thought about. So we've been basically taking inspiration from these organisms in nature and trying to replicate it into our own materials. But we never actually thought about substituting these organisms in nature. But what I think is interesting is actually look at the tasks that these organisms are performing in their natural environment and try to see how we can use their functionality in man-made applications. So I don't think it would be much of a substitution, but as well as learning how they perform these tasks and then trying to find applications that would benefit or solve any problems that we have currently.
Okay. Well, that's my question. I mean, I have a whole bunch, but I'm not going to ask them all because the audience have lots of questions. So I will turn it over to you to have a look at the long list of very interesting questions that have come in from the audience for you to maybe provide some answers on.
Right, so I see a question. So to what degree are these soft robots real robots doing the dirty, dangerous, and do work? So at the moment, soft robotics is still, let's say, gaining attention into real-world applications. And for our robots, so the robots that we have developed in these studies, they are not really used yet in any kind of applications. But like I said, they could be used in dirty work such as water purifications and help us perform these tasks. So the second question, so how big and how small can the soft robotics be? And what is the range and what is needed in order to expand the range? So that's a very good question, and it's something that we have been working on. So how small can we make these robots? Right now, so they're around centimeter range, 1 or 2 centimeters. And it would be interesting to both go smaller and bigger. So going smaller would have many advantages for microfluidic devices or even biomedical applications in which if we extrapolate to the future, we could have soft robots in our veins to deliver drugs. So it is very interesting to go small, but there are difficulties in the fabrication procedure. And there are a few research groups working on this to use different kinds of laser techniques to create these robots. And currently, if I'm not mistaken, they're around the micron range. So people can already make micro-scale grippers that can be steered by light or magnetic field to grasp cargoes. And then how big they can go, well, that's, I think, also a room for imagination. From what I know, I have not seen yet bigger robots, and I don't see, for us, I guess we could scale the current robots to factor 2 or 3, but much bigger than that, I think we're going to run into problems. So are the frequencies of light relevant? If so, to what extent? Right now, we use to use light to trigger these mechanical deformations. What we're concerned with mainly is the wavelength of light. And why? Because the chromophores that we're doping into the polymer films, they absorb certain wavelengths of light, and we're not per se looking at the frequency. So because of the molecular absorption of these dyes, the wavelength for us is the most interesting part. So that by using different wavelengths of spectrum, we can drive change in specific areas of the device. So it would be very interesting to look into devices that have one section that's responding to UV light and the other section that's going to infrared, so to have very distinct bands of absorption so that the same device can be steered by having different light sources that will trigger different kinds of deformation. Another question, so have specific user groups showed interest so far? What kind of potential functions do you and others envision? Specific user groups, I guess this is more like what kind of industries would be interested. And I think at the moment we're really in the development stage. We're showing the potential of these materials in certain areas. And they're not per se ready to be implemented in any applications. But I think if research stays or keeps on going at this speed, we may see in the future applications then linked to biomedical or microfluidics. I think these are really interesting applications which will come up in the future. So another question, to what extent is the light-driven principle the same as in artificial cells that are light-driven as well? What can the two fields learn from each other, from one another? So I think there's a lot to learn, and I think the cross-collaboration between different groups will lead to many fruitful discussions and new materials. So in our group, we're really in contact with the mechanical engineering group of Jaap den Toonder, and this has already led to a lot of developments in trying to translate the small molecular motion that we as chemists know and understand into the macroscopic movement of devices. And I think the same would go then for more biologically focused groups, that we can learn from each other and maybe use cells in our applications. How did you wind up in this particular field of research? Well, it's a good question. So in our group, we're focused on using stimuli, such as light, heat, humidity, or magnetic fields, to try to drive changes in materials. And these changes can be mechanical deformations, but also they can be photonic changes. And for me, I was always interested in seeing things move. So it is quite magical that you shine light on a material and it starts moving. And I think that for me, that's what intrigued me and led me to continue in this field. So that was my motivation to do this, and to see how far we can show that these materials can be used to perform functions. Yeah, these were, I think, the questions.
I think that's the questions. I have one more question, maybe if we have time, I could just ask this, because I just want to look at a specific number you mentioned. You mentioned that your walking robot was able to carry 20 micrograms. What is the largest mass?
So 20 micrograms, that's the mass of the robot itself.
That's the mass of the robot. Yeah. What was the size of the cargo mass of the cargo that was carried, and what is the largest cargo it can carry?
So the cargo in the video, it's 5 micrograms, I believe, for this one. We haven't actually tested the full potential, so we should do follow-up experiments in which we load it up until we see how far it can go. But I don't think it can carry much more weight. And this is then coming at the cost of the mechanical properties of these materials. So if we can make them more robust, we may be able to, let's say, carry bigger cargos and make the material more rigid. And then we can use it for also different applications.
And one last question. I thought it was really interesting that you refer to the idea of using these soft robotics for the delivery of perhaps even medicines or drugs inside the body. So, of course, how would you activate them with light if you were to use such a light-driven soft robotic for that function?
Yes, so this is one of the, I see it as one of the biggest challenges for these type of soft robots in the field, if we would ever use them in biomedical applications. So now we're using usually UV light to drive this deformation. And UV light in combination with cells, not very good idea. So one of the fields of research within these smart films is to use different kinds of wavelengths of light to drive this deformation. So one interesting part of development can be using infrared light, which then can be used also in our body to drive these deformations.
Okay, so that there are options there. You've already looked at it, and is that somewhere, if you were to continue with this type of work, you'd like to go towards that type of application, or would it be something else you'd like to look at?
So I think the combination, so to bridge the two fields, so soft robotics with biomedical applications, that being drug delivery or microfluidics, organ on a chip applications, this is definitely a step that needs to be taken. Yeah.
Okay, and what does the future hold for you then?
For me? So if I would stay within the field, this is definitely a part of research that I would like to go into. really bridging the gap between these two fields and work into maybe drug delivery systems, or really go for the dream of having these soft robotic devices deliver and transport cells. I think this would be my goal.
I can think it's a really nice goal. I think it's a nice application, and it can have a huge benefit in terms of society as well. I just want to say thank you very much, Marina, for presenting your very interesting work. And just to clarify, you're very close to finishing your PhD at the moment, right? Is that correct?
Yeah, indeed. Should be in 3 weeks. Yeah.
Well, 3 weeks. So you've got your defense in 3 weeks?
Yeah, defense in 3 weeks.
Okay, well, the very best of luck with it. I hope it goes really well.
Yeah, thank you very much.
No problem. Marina, thank you very much for contributing to the Stories of Change on this Friday afternoon as part of Dutch Design Week 2020. And please stay tuned for additional Stories of Change that are going to be online later on this evening. And there are going to be 2 different topics spoken about on the YouTube channel for the Stories of Change, Drivers of Change at TUE. And one of the topics relates to new hope for babies born at the border of viability. And the second talk is related to lightning strikes thrice, breaking Thunderbolt 3 security. So 2 contrasting talks, but also 2 fascinating topics, I'm sure. And please be sure to tune in to both of those presentations as part of the Stories of Change and the Drivers of Change of TUE for Dutch Design Week 2020. Thank you very much for tuning in to this Stories of Change with Marina's fantastic presentation on soft robotics. I've been Barry Fitzgerald, and hope to see you again soon. Thanks very much.